Hello everyone, this is my video for recitation 9, which is about properties of sets. Yeah, I couldn't make it to my recitation, so I'm gonna post this video on Piazza. But yeah, let's get started. So we're in chapter 6.2, and the first question says, for all sets A and B, A union with the intersection between A and B equals A. So if you remember, to prove something like this, we need to first prove this side equals this side first, and then after that we prove the right side equals the left side. So we'll do the first case first. We'll just do the left side first. Alright, so A union with the intersection with A and B, this just means X is either an element of A or X is an element of A and B. Right, so we have two cases here. Since it says or here, we could basically break this up into like case 1, then case 2. Right, so we'll begin with X is an element of A. So when we have multiple cases like this, what you want to do is prove that each case goes to A. So the ultimate goal here is to prove that X is an element of A, and the ultimate goal of this one is also to prove X is an element of A. So the first one's pretty easy since we already have X as an element of A. Like, it's all obviously, clearly, X is an element of A. So you can't really do much there. It's literally what we want to prove. So next one is X is an element of A and X is an element of B. Right. So X is an element of A and B just means X is an element of A. We can just write it like that. And the intersection between A and B is just a subset of the set A, right? So let's just call this as A and this is B. Then this will be the intersection between the two. And if we just look at A alone again, what we just highlighted was basically like this part of A. So obviously A intersection B is a subset of A, right? So from that we could say, since A intersection B is a subset of A and X is a element of A intersection B, X is also an element of A. So we proved that as well. So this is good for the left side, proving the left side is equal to the right side. Now we need to prove the right side equals the left side. Right, so now we say alright, so now we're going to do the right side, where we prove that we know that X is an element of A, and we want to prove that X is an element of A union intersection with B, right? Okay, so we could do this by, so we know that X is already an element of A, but A itself, the set A, is a subset of A union A intersection B, right? Because A union, so let me just do this graphically. A union A intersection B, this whole thing would be A, this whole thing would be A, and then the intersection would be this stuff in the middle, right? So obviously that constitutes, A is a subset of that, right? Because it's just, this is A and then A union A, or A and B is the dark part plus the light part. So A is a subset of that. So we know that if X is an element of A and A is a subset of that, then X is also an element of A union A intersection B. And yeah, that's a sufficient proof for that question. Yeah, that's about it for that one. Alright, on to the next question. Next question says, for sets A, B, and C, we need to prove that the Cartesian product between A and B union C equals A times B union A times C. And there's an equal sign here, so we need to prove the left-hand side equals the right-hand side first, and then the right-hand side equals left-hand side. So let's start with the first one. Okay. So we're starting with A times B union C. So this means XY is an element of A times B union C, and X is an element of A, and Y is an element of B union C. So since we have this union here, we're gonna run into cases again. So the case will be Y is an element of B, or Y is an element of C. And this X is an element of A stays constant. So let's start with the first case where Y is an element of B. Right, so we have that X is an element of A and Y is an element of B. So from these two, we could just say XY is an element of A times B. And right, so if you remember, we're trying to prove that everything, in the end of this, we basically just want to prove that X is an element of the right-hand side, which is all this, right? So we can see that A times B is included in the union with A times B. Sorry, I'm about to say. So we have this on the right-hand side. And we just derive this, right? So when it says the union, it's or. So once we derive one part of it, once we derive one part of the union through the inclusion of union property, we can say that XY is an element of A times B or A times C. Yeah, so once you get one part of the union, you could immediately say that it is that element is so we have, let's say X is an element of set A, right? Once you have this, you can immediately say X is also an element of A or B, because it's an or. It's not constricting like and. It could either be an A or B. So once you have this, you could say that right after. Okay, case 2, where Y is an element of C. So we have that, one sec. Alright, so we have that X is an element of A still, and Y is an element of C. So XY would be an element of A times C, which is once again part of the unions right here, right? So based on what I said before, you can immediately conclude that XY is also an element of A times B union A times C. Right, so we proved this for the left-hand side. So now let's do the right-hand side. So now we want to prove that X is an element of A times B union C. So here we have that X is an element of So since we have a union here, there's a union, we break this into cases once again. So case 1 would be X is an element of A times B. If X is an element of A times B, we'll say XY. This means that X is an element of A and Y is an element of B. Okay, so B itself is a subset of B union C. So since Y is an element of B and B is a subset of B union C, we could say that Y is an element of B union C as well. So since we have X is an element of A and Y is an element of B union C, we could say XY is an element of A times B union C. Alright, so that's good for that case. Let's do the second case, where XY is an element of A times C. So X is an element of A, and Y is an element of C. And C is a subset again of B union C. So once again, we can make the same claim that Y is an element of B union C. So X and Y, since we have X is an element of A and Y is an element of B union C, we can say X and Y is an element of A times B union C. So now we proved the left-hand side is equal to the right-hand side and the right-hand side is equal to the left-hand side. Alright, next question. Alright, number 25. Use the element method for proving a set equals the empty set to prove each statement in 25 to 35. Assume that all sets are the subsets of the universal set. So we have for all sets A and B, the intersection between A and B, and the intersection between A and the converse of B is the empty set. So we could just when we look at this, it's basically saying x is an element of A and B, also, and x is an element of A and B, the converse of B. So we could break this down even further and say x is an element of A and x is an element of B. Also, x is an element of A here, and x is not an element of B. So when it says B converse, that means everything not in B, right? So we could clearly see that there's a contradiction here, right? So x is an element of B and x is not in B. That can't happen. So since there's this contradiction, so the intersection between the two sets will be the empty set. Yeah, so whenever you run into something that contradicts each other, it's gonna come out to the empty set because that can't happen. All right, next question. One sec. I think I skipped a couple questions by accident. Oh yeah, I skipped a couple. Alright, so we'll just go to 47 first. Alright, 47 says, one sec. Yeah. Okay, so given sets A and B, the symmetric difference of A and B is denoted as A triangle B. So that basically is A minus B union B minus A, right? So now it wants us to prove that these both are the same. So we can just write that out. So A and B is right. So then B triangle A would be B minus A union A minus B. Okay, so now we could just look at the elements and see if they're equal. So this would be here, it would be x is an element of A and x is not an element of B, or x is an element of B and x is not an element of A. So that's this guy on the left. The right hand side is x is an element of B and x is not an element of A, or x is an element of A and x is not an element of B. So if we just say this is A, okay, let's just say different letters. Let's say this is set X, this is set Y. They're connected by the union. We see that X would be this one, and then y would be this one, and we have a union here. So it's basically, if we simplify this, it would be x union, we're seeing if x union y is equal to y union x, and these are the same. X union y and y union x are the same due to the commutative law. Right, so that proves that both of those are the same. Alright, next question. It says, now we're doing it with the empty set. So A triangle empty set equals A. So this would be, so since A triangle B is A minus B union B minus A, if we just substitute the empty set for B, it would become empty set minus A. So if we use the set difference laws, which says that A minus B equals A union B complement, we could turn this into A intersection with empty set complement union with empty set intersection A complement. And the intersection of the empty set is the universal set. So this actually comes out to A intersection with the universal set. And then this will come out to the empty set. Because the empty set cannot share elements with any set. So this will always come out to the empty set. And union with the universal set, the intersection with the universal set. So this would be A, and then this would be the universe. The only intersection would be the set itself. So this comes out to A. A union with the empty set is just A. So we proved that. So yeah, that's a sufficient proof. So let me get the other problems as well. I missed out on 28 and let's see. $27 and $33, I think. And 28. Okay, we'll just do those now. So 27 this is chapter 6.2. Then this is 27. It says for all subsets A of the universal set U, A intersection with A complement is equal to the empty set. Right, so if we just look at the elements here, this would say that x is an element of A. This says that x is not an element of A, which is again contradictory. So the intersection would result in the empty set. Yeah, so it's clearly going against each other. A intersection with A complement is saying that, okay, X is an element of A, and then X is also not an element of A. Doesn't make sense, so it comes out to the empty set. All right, next question, number 33. Okay, so this says that for all sets A, B, and C, if C is a subset of B minus A, then A intersection C is equal to the empty set. Right, so if X is an element of C, right, so, and C is a subset of B minus A, that means that X is an element of B and is not in A. Right, so let's say so let's say we have our sets A and B. A and B. So B minus A would be everything in B except A, right? So let me do this another color. This would be B minus A. And then now we're saying C is a subset of that. So it could be like just this little part. And it follows the same rules, that it's an element of B, but it's not an element of A, right? So if X is an element of C, so now, if we look at A union C, A intersection C, this says that X is an element of A, and here we know that X is not an element of A. so this is a contradictory. Yeah, this is contradictory, so this comes out to the empty set. Yeah. And I missed another one, which was 28. Alright, so now we'll do question 28. So they originally gave this a bunch of... They're trying to prove this, and they basically gave the proof, but we need to walk through every step and say why they did something. Alright, so this was basically the difference of sets thing I was saying before, where A minus B equals A intersection with B converse. So yeah, that's essentially what they did here. So the reasoning here would be difference of sets. Alright, so then the next step they did was the right hand side was A union B intersection with C union A converse, and put all that in the converse as well. So they just did the union the difference of sets once again, where they turned C minus A into C intersection A converse, and then that was already in a, sorry, I keep saying converse as a complement, and then that was already in a complement, so they kept the outer one. So this is once again difference of sets. Then they said the right hand side was A union B intersection with A complement union, intersection C. That's all in a complement as well. And then they're just changing the order. This is just the commutative law, right? And then the next thing they said was A union B intersection with A converse, A complement union C complement. And this is just De Morgan's laws. Because he's basically like they're basically distributing this to everything, even the intersection. Yeah, that's De Morgan's laws. That's the result you would get after that distribution. And then they said this comes out to A union B intersection with A union C complement. And this is just the double negation. Double complement law. So if you just take something already raised to a complement and then complement it again, it's the same set. Then finally then they say A union B intersection C complement. Yeah, so this was basically, it might not be so clear, but that is the distributive law. Kind of backwards though. Yeah, like originally you would start with this and then you would unfold it into that, but they just went backwards. But it's the distributive law nonetheless. And then lastly they say the right hand side is A union B minus C. And then they basically did the difference of sets backwards. Like you would originally have B minus C and then say B intersection C complement, but they just went backwards this time. So yeah, that's the answer for this question. Oh yeah, pretty sure that's all. So yeah, that's all for this recitation.